All right, general chemistry students, let's do this. We are talking about ionic compounds now. Our last video, we talked about naming them. And before you've watched this video, hopefully you've already gone in class and you've done page 7 of your classwork, of your unit packet. So let me just show you what that looks like, and then we will dive right into the notes. So there's this really amazing video that I think explains how to write ionic formulas really well. It's by Tyler DeWitt. You can find it at this YouTube address. It is also linked in Teams, probably in one of my posts. You can definitely find it on my YouTube playlist. So if you watch his video and you go through, I made a typo. It's lithium oxide, not lithium chloride, but you get that. I make tons of typos. But yeah, if you go through his video and follow him, he's going to give you all 4 of these as examples. And then you all can kind of figure out what are the most common mistakes and how do you do this. These subscripts in the formulas are really important. And yeah, this will be really useful for you. So if you've already done this, then this probably already is making some sense to you. So, but let's keep going and have some notes just for the future. Okay. So for writing ionic formulas, before we really dive into these notes, now that I've introduced that, there's one more thing we should talk about. I want to give you a visual representation of ionic compounds. So before this, we were doing Lewis electron dot models of compounds. Those are for covalent compounds, and covalent compounds are different than ionic. The main thing is that covalent compounds share electrons. So when you draw them, for example, if you're drawing water, you have oxygen in the middle and the 2 hydrogens that are connected by lines. Those lines indicate that the oxygen and hydrogen are sharing electrons. That's not true with ionic compounds. That's only true with covalent compounds. So let's go through this visual and hopefully this will help make sense of it. So this right here, I made this a couple of years ago in PowerPoint. I'm really proud of it. So let's go check it out. This is sodium chloride, also known as table salt. So this is what table salt looks like. And if you were able to zoom in and just look at the molecules at the atomic level, it would look something like this. We've got this lattice, this sort of grid shaped, where every other atom is a sodium or a chlorine. The sodiums are positively charged and the chlorines are negatively charged. The electrons that are around the chlorines, those are actually around the chlorines. There's no valence electrons around the sodium because they've been given away. So let's watch how this was formed. The important thing to remember here, this is all about ratios. So let's go through the process. Okay, so when you are making sodium chloride, you have a sodium atom and a chlorine atom. The sodium atom has only 1 valence electron. The chlorine has 7. So the sodium can give away its electron to the chlorine. So the metal donates its electron to the non-metal, sodium to chlorine. When that happens, the metal becomes a cation, 1 positively charged, and the chlorine becomes an anion, it's negatively charged. That transaction is complete. This is the big difference between covalent and ionic compounds. Covalents don't give away electrons. Covalent bonds, they share electrons. In this case, it's completely given away. Now we have these 2 ions, but you know how like the positive and negative sides of a magnet are attracted to each other? The same thing is true here. We call it an electrostatic attraction, but as soon as you have a positive and a negative, they are attracted to each other. It's sort of like magnets, but more like static electricity. Like if your clothes get all staticky, they'll stick together. It's the same basic concept. So now these 2 are attracted to each other and will stick together. And this forms the compound. As a whole, they're neutral because 1 is a positive and 1 is a negative. When this happens, it doesn't just happen between 2 chlorine, one sodium and 1 chlorine atom. It doesn't just happen between 2 atoms. It happens to lots of them, and they form these complexes. The important thing here is the formula for sodium chloride is NaCl because for every 1 sodium, there's 1 chlorine. It's the ratio of the 2. There can be, millions of them. It doesn't matter, but for the ratio is always 1-to-1, 1 sodium for every 1 chlorine. Now, that is frequently the case with ionic compounds, but not always. So let's take a look at another example. This is sodium oxide. Sodium oxide's formula is a little bit different. If you see, it has a very different texture. It's like this fine white powder. I think you actually use this to make plaster of Paris, if I'm not mistaken. But anyways, if we were to zoom in on this, it looks really different. So looking at this, well, how many sodiums are there and how many oxygens? So if you're counting, there are 10 sodium ions and there are only 5 oxygen ions. So that means that for every 1 oxygen, there's 2 sodiums, or it's a 2-to-1 sodium to oxygen ratio, which is exactly what this formula is telling us. So it's all about these ratios. With ionic compounds, there's only one possible ratio that will ever work. So you can always solve for it, and you always are going to have to, which is exactly what you did in the video. So if I say sodium oxide, I know right away it's Na2O. You'll get to the point where you'll know it too, just that quickly. So let's go through the process. So it's the exact same thing as before. We have a sodium, neutral sodium atom and a neutral oxygen atom. The oxygen has 6 valence electrons, so it needs 2. The sodium has 1, so it wants to get rid of it. So that's the first thing that happens. Okay. Now they're both ions. The sodium is good to go, but the oxygen still needs another electron. It's only a 7. So if another sodium atom happens to come along, it can give its extra electron to oxygen. Now, the oxygen has a full octet. The sodium has gotten rid of the only one left in its octet, so the next octet down will work just fine. And we now have 2 sodiums. One is +1. The other one is also +1. We also have 1 oxygen that has a -2 charge. They're, again, going to be electrostatically attracted to each other, something like that. As a whole, this is still neutral. Even though there's 3 different ions, because it's a +1 and a -2 and a +1, those all add up to be 0, neutral, nada, which means that we've done this correctly. And again, when you have a whole bunch of them, they'll arrange themselves something like this. Okay, so hopefully that visual helps this make a little bit more sense and give you some context. So let's just go back to the notes and we'll do a little bit of practice. All right, so the notes already have a step-by-step process written out for you. So the first thing that you're going to do, let's actually go through it together. I have 3 different examples here. I like to use the exact same method from what Tyler DeWitt did in his video that we watched. So we'll go through it together. All right. So the first step is to write the symbol and charge for the anion and cation next to each other. So calcium is the cation. We're going to find it on the periodic table. So calcium is here, and according to our table, from what we've written before, that's a 2+ charge. You'll remember from ion symbols, you always make the pluses like a little superscript like that. Okay, fluoride is fluorine, which is an F, and that's a -1. Okay, next step. We can't mess with this. We can't change the charge. Calcium is a 2+ charge. Fluorine is a 1- charge. We can't get rid of anything. It's at the very, very minimum. There's at least a 1-to-1 ratio, but maybe it's not a 1-to-1 ratio. We have to check and make sure that all of the pluses and all the minuses add up. Right now they don't. There's 2 pluses and only 1 minus. So we're going to have to add another minus to balance this out or to neutralize it. I like to use the word neutralize. He uses the word balance, but I like to use the word neutralize. It's the same idea. There's a reason, but it's okay. Okay, so I'm not going to add another calcium because that wouldn't help, but an extra fluorine would. Okay. So now, if we're looking at the charges, let me grab, this will work. Let me get a blue one as well. We'll see if it shows up on this paper. Okay, so I sometimes will make a little chart off to the side like this with the pluses and the minuses on them. So when we first started, the calcium here has a 2 plus charge, and the fluorine has a 1 minus. So when we first started, there was 2 pluses and just 1 minus. It's no good. But if we add a second fluorine, we now have a 2. Our charges are now neutralized. They both will work out to equaling 0. So now to write the formulas. So we've done number 2, add more cations or anions or both until the negative and positive charges are equal. Count the number of each ions it took to be neutral. So it took us 1 calcium and 2 fluorines in order for this to be neutral. Next step, write the symbol for the cation with the total number from step 3 as a subscript. So calcium goes first. It only took 1. So we could put a 1 here. That's totally okay. But because we're chemists, we tend not to. We're super lazy and we just like say, if it's just 1, just leave it be. So unless it's a 1, we ignore it. We write it down unless it's a 1. Okay, next step, write the symbol for the anion with the number from step 3. So here's the symbol for the anion, and it took 2 of them. So as a little subscript, we're going to put 2. So the formula for calcium fluoride is CaF2. And that right there is our answer. All right? Cool. Let's try the next one. All right. You can always try this one first, like pause the video and see what you get, and then you can check with what I've written. That could be a good idea. Okay, magnesium sulfide, first step. We got to find it. Magnesium is here. It is a +2 charge. Sulfide is over here. If we go up, it is there you can see it, a -2. So let's do our little, I'm going to do that little table-y thing off to the side, just because I kind of like it. Can be useful. Sometimes it's good to have a visual. Okay, so we've got our positives and our negatives. So Mg is a 2 plus. So we've got 2 in the positive category, and S is a 2 minus. So we've got 2 in the negative category. So the question now is this neutral? Do we need to add any magnesiums or any sulfurs in order to make this neutral? The answer is no. It's good. It's good to go. There's 1 magnesium, there's 1 sulfur, +2 -2 equals 0. We're good to go. So we don't have to do anything else. All we have to do now is write the symbols, MgS. So this tells us that the ratio in this particular ionic compound is for every 1 magnesium, there's 1 sulfur. This one says for every 1 calcium, there's 2 fluorines. It's all about ratios. All right. So I actually can, maybe I'll draw that really quickly just for fun. Just so you can kind of see it. Again, that's the ratio. Pretty cool, right? Okay, magnesium and sulfur, for every 1 sulfur, there is 1 magnesium. Yeah, all neutral now. All right, let's do the last one. Why don't you guys try this one out yourself, for sure. See what you get. All right, let's go through and make sure you all got the right answer. I like to use red for minuses and blue for positives. It's just my thing. I use green for neutral. It's just something I've gotten used to. I try to like code it into your head. So whenever you see red, you think negative electrons. Whenever you see blue, you think protons are positive. Neutral is neutrons. It's green. It's great. Okay. So this time we've got strontium and phosphide. So let's find strontium. Strontium is here. It's Sr, and it's a 2+ charge. So that's the first step. Next step, let's find phosphide, which is phosphorus, which is here, which is a -3. Okay, so right now we've got 1 of each. So that is going to give us 2 in the positive column, but only 3 in the negative. So that's no good. So how do we do this one? Well, my general strategy for this is Whatever there is not enough of, let's add more of that. So it looks like we don't have enough plus. We have too much minus. We can't add like a +1 here. It's just not possible. We only have strontium, and strontium is a +2. We can't change that. But what we can do is we can add another strontium. Okay. So now we have 2 strontiums, so they're both 2 positive, so the total is 4 positive now. Okay, so that doesn't really look like it helped all that much, did it? So now we've got too much plus and not enough minus. So we got to do it again. We'll just have to keep going until it eventually works. So let's add another minus. We can't add a -1, doesn't work that way, but we are allowed to add another phosphorus, which is a -3. So now we have -3 and -3 is -6. So we've got -6 charge. So we still haven't fixed it. We've got a 4 and a 6, but this is where it starts to make sense. This is that least common multiple, lowest common denominator thing, whatever it is that you guys talk about in math. I can never remember. If we add another strontium, now we have 3 of them. 2, 4, 6. 6 positive. Okay. Now the charges are balanced. They are neutralized, is what I mean. The charges are neutralized. We've got a total of 6 positive and a total of 6 negative. So we can now write the formula. So the formula is going to be this a strontium. There's 1, 2, 3 of them. So we put a little 3 down here to represent that. And there's P for phosphorus, and there's just 1, 2 of those, so 2. So the formula is SR3P2. Okay. Pretty cool, right? So one thing to keep note of is the fact that these little pluses at top, they're the charges, they're not included in the formula because the formula itself is neutral. But you have to use those charges to help you figure out what the formula is. So this one is going to have a slightly different ratio if I'm going to draw out the pictures, which I totally can. So this one's the ratio, again, for every 2 strontiums, there are 2, every 3 strontiums, there are 2 phosphates, sorry, excuse me. So you could take this little pattern here and, replicate it as many times as you want, and that would represent what the molecule, what those little grains of salt or like powders that you find in a chem lab actually look like. Okay. All right. So hopefully that was helpful. This section, there's a reason we're spending so much time on it and explaining it so many ways. It can be a little abstract. It can be a little tricky, but it's really, really, really important that you learn this and that you're able, if I give you the name, you have to be able to tell me what the formula is correctly. When we get to the next unit, you got to be able to do this. When you get to pretty much every unit from now on, formulas are super, 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 super important. So if this makes sense to you, that's awesome. We're going to keep practicing these. Aside from this page 7 in your packet, there's also, you can now do page 8. So page 8 in your packet, I already assigned you these last 11 through 20 when we were just writing names. So writing names is pretty easy. Now you are able to do this writing formulas. You can check your answers with this later. There will be an answer key available. But yeah, the other half you can try yourself. Definitely make sure you can do all of those. All right. There's only 2 more topics that we have to add to this, which is transition metals and polyatomic ions, which are just some details. But really, this is the big heart of the unit. If you get this, you understand mostly what you need to know. So that's all I have for you for now. Be excellent to each other, and I will catch you next time.